Welcome to The Explainer. So today we're going to talk about one of the most fundamental ideas in all of artificial intelligence, loss functions. This is really the secret sauce that lets a machine figure out when it's made a mistake and, more importantly, how to learn from it.
So let's just jump right in with the big question, right? We all know that machines learn from data, that they get smarter over time. But how? How does a machine actually know it's messed up? How does it measure its own errors so that it can improve? Well, it really boils down to this. It needs a way to keep score. The whole learning process is built around this pretty clever mathematical tool that's basically a scorekeeper, and it doles out a penalty every single time the machine makes a mistake. And that scorekeeper has a name. It's called a loss function. Its job is, conceptually really simple. The bigger the mistake the machine makes, the higher the penalty score. So the goal, always, is to get the lowest score you possibly can. To put it a little more formally, a loss function measures the loss, you can just think of that as the error, between what a model predicts and what the real true answer is. So it takes this kind of fuzzy idea of getting better and turns it into a very concrete mathematical goal. Just minimize this score. But here's where it gets really interesting. The scoring rules, they change depending on the kind of game the machine is playing. I mean, you wouldn't use the same rules for chess that you'd use for soccer, right? It's the exact same idea in AI. And you can pretty much boil machine learning tasks down to two main flavors. The first is what we call regression, and that's all about predicting a specific number, like the price of a house. The second is classification, where the goal is to pick the right label, like figuring out if an email is spam or not spam. Okay, so let's tackle that first game, regression, predicting numbers. One of the biggest challenges here is how you deal with outliers, those weird, extreme data points that don't quite fit. And different scoring rules have totally different philosophies on how to handle them. So for instance, you've got mean squared error, or MSE. Because it squares the difference between the prediction and the truth, it punishes big mistakes like exponentially. It's super sensitive to outliers. So think about it. What if you have a typo in your house price data? A tiny apartment is listed for $10 million. MSE is going to freak out over that one mistake. On the other hand, you have mean absolute error, MAE, which treats every error proportionally. It's way more robust to that typo, but it might not be quite as precise overall. So right away, you see there's a strategic choice to be made. What kind of mistake do you want your model to be most afraid of? And this is where a third option, Huber loss, comes in. And it's a brilliant balance. It basically gives you the best of both worlds. It acts like the very precise MSE for small, everyday errors, but if it sees a huge error, it switches over to act like the more robust MAE. So you get accuracy and stability. All right, let's change gears and talk about our second game, classification. In this game, scoring isn't just about being right or wrong. It's also about how confident the machine is when it gives an answer. And a super popular way to score this game is with something called cross-entropy loss, which is all built around this one simple but really powerful idea. It rewards confident, correct answers, and it harshly penalizes confident, incorrect answers. Okay, let's make this real. Imagine the model's job is to look at a picture and decide if it's a dog, a cat, or a bird. The real answer is dog. The model looks at the picture and says, I'm about 70% sure it's a dog, maybe 20% a cat, and 10% a bird. That's pretty good. So, because the model was on the right track and pretty sure about it, its cross-entropy loss score, that penalty, is really, really low. It did a good job. But what happens if the model is super confident and super wrong? So let's say it looks at that same picture of a dog and says, I am 80% sure that's a cat. Well, in that case, the penalty score just skyrockets. The model is being punished not just for being wrong, but for being so certain about the wrong answer. Okay, so there's another way to play this game using something called hinge loss. And this one's a little different. It doesn't just want the right answer. It wants the right answer to be correct by a nice, wide, comfortable margin. Here's the key takeaway for hinge loss. It penalizes two different things. First, being flat out wrong. And second, and this is the interesting part, it penalizes you for being right, but not right enough, for being too close to that dividing line where you might have guessed the other way. Let's use a spam filter to see how this works. Case 1. An email is definitely spam, and the model confidently says, yep, that's spam, with a high score. Hinge loss gives it a perfect score, 0, no penalty, job well done. But now, case 2. The email is spam, The model correctly identifies it, but it's a little hesitant. Its confidence score is weak, kind of close to the not spam line. In this case, it actually gets a small penalty for not being sure enough.
And then, of course, you have case 3, the worst case scenario. The email is spam, but the model gets it totally wrong and says it's not. That's when it gets hit with a high penalty score. So look, the big takeaway here is that choosing a loss function isn't some tiny technical detail. It is a huge strategic decision you have to make when you're building any AI system. You are, quite literally, defining the rules of the game. It's defining what success even looks like for the AI. By picking one scoring method over another, you're guiding its entire learning process. You're shaping what it pays attention to, what it prioritizes, and what kinds of mistakes it's going to work hardest to avoid. And this really leaves us with a fascinating final thought, doesn't it? The rules that we set for our machines, they're a reflection of what kinds of mistakes we as humans are willing to live with. So, when teaching an AI, what's worse? For it to be confidently wrong or just plain unsure? The loss function is where we embed that choice.